Amid the swirling vastness of galaxies, each a cosmic city of stars and planets, the silence raises a compelling question. Could the very nature of galaxies themselves hold the key to why intelligent life remains unseen? The Fermi paradox explores a profound question. If the universe is so vast and old, filled with countless stars and potentially habitable planets, why haven't we encountered any signs of intelligent extraterrestrial life? Or as Enrico Fermi famously wondered, where is everybody? This was back in 1950 and sparked debates and scientific inquiries into the apparent silence of the cosmos. Given the sheer probability of other civilizations arising in our galaxy alone, the lack of contact or observable evidence presents a puzzling mystery that challenges our understanding of life's prevalence and development in the universe, and we've considered a number of explanations in various episodes over the years. One possible explanation lies in the concept of filters, significant barriers that prevent life from reaching advanced stages of development, or, in some cases, from arising at all. These filters could act on a planetary, solar system, or even galactic scale, wiping out or severely limiting life's chances long before it reaches the capacity for interstellar communication with us. Filters may include natural cataclysms, evolutionary constraints, or resource limitations that cull potential civilizations or prevent them from ever emerging. The study of filters helps scientists hypothesize why intelligent life may be rare or absent, offering insights into the cosmic challenges that might await any aspiring civilization. On this show, we usually classify these filters into categories of when and how much, with early filters being those that would kick in before life had developed, or while it was very simple, like a planet being too hot, while late filters are those which humanity has yet to reach, like killing ourselves from wrecking our world or unleashing AI mortarbots to wipe us out. And there's a host of filters in between, the middle filters that life needs to survive or to pursue certain pathways, like intelligence and technology. Then we categorize by severity, lesser, minor, major, and greater filters, where a lesser filter might be even odds, a minor filter something only a few % of examples would pass, major being those that maybe only 1 in 1,000 might survive or pursue, and great filters being those that might as well be lottery odds or worse. Often a great filter can be decomposed into a number of associated filters, such as whether or not a large moon is necessary for life, and we looked at that a few months back and found that there were a number of lesser and minor filters attached to the moon, many unrelated beyond that. We've done similar in considering if our sun might be a particularly good candidate for life in our episode Rare Sun, or if the basic conditions of Earth or the solar system might be beneficial for life. Today we'll be focused on the sorts of filters that come from the galactic scale of things, and see what those might be, and if one of them, or the collection of them, might qualify as a great filter. And to do that, we should probably talk about what a galaxy is and how they formed. You probably already know that galaxies are huge collections of stars, and the one we live in is the Milky Way, and the nearest one is Andromeda, but that's only superficially true. The period of time that stars will form in this universe is about 100 trillion years, trickling off after the first 2 trillion, and we are only 14 billion years in that period, less than 1% of that primary star formation period, and just over 1% of the whole stellar era. So the game is just beginning. Most stars will live much longer than our sun too, hundreds of billions if not trillions of years. Only big ones our size or larger die in mere millions or low billions of years. Of stars smaller than ours, only the oldest examples of those just a bit smaller than our sun will have died yet. No orange or red dwarf, which is most of the stars in this universe, has ever died of old age. I want to emphasize that because the nature of Hubble expansion in our universe means that by roughly the year 150 billion, all galaxies will have merged into each other with their local neighbors, while the space between those clumps will have widened so much that we won't even be able to see the other galaxy clumps anymore. These aren't superclusters either. Superclusters are hundreds of thousands of galaxies. These clumps might get that big in some cases, but our own will only be a few dozen at most, and our own supercluster will have torn itself apart by then. Were you to arrive on the galactic scene around then, as opposed to today, you would still be able to see the wispy telltales of those other galaxies, and some flotsam and jetsam of ejected black holes and stars out beyond the galaxy. But there will only be one galaxy, what we sometimes refer to as the Milky galaxy, though it will also include the Triangulum galaxy and many smaller dwarf galaxies of our local group, and mass about 2 to 3 trillion solar masses. This is the reality in which most stars will be born, and these merged galaxies will range in mass a lot, as some will be from much bigger or smaller clumps. Indeed, some might be isolated dwarf galaxies of less than 1 billion stars. All islands by themselves though, and even now, most galaxy groupings look like archipelagos of many small islands and a handful of bigger ones. Galaxies weren't well defined back then, lacking the shape we associate with modern spiral or elliptical galaxies, and were closer together. We can see them, as astronomy is history, and if we look many billions of light years away to 13 billion years ago, we see a universe of these proto-galaxies. We can look even closer to Earth and see a clear timeline of galaxy formation and development. The period we live in is one in which a lot of these early proto-galaxies are merging or getting gobbled up, sometimes leaving behind ejected dwarf galaxy cores who a bigger galaxy pulled the disk off of. Our galaxy is not simply made of earlier mergers, it is in the process of consuming several other galaxies even today, and the Andromeda and Triangulum galaxies are both doing the same, and all three will merge about the same time, beginning in just a few billion years. The merger will take billions of years too. There's also not much to delineate extragalactic space from galaxies either. There are plenty of stars between us and Andromeda, and even whole star clusters, but many of these were ejected violently from galaxies, often during merger events, and may lack planets as a result, or be low in metallicity and rocky planets, a point we will return to. Early galaxies were markedly different from those we see today, forming only a few 100 million years after the Big Bang. These proto-galaxies were small, irregular, and composed almost entirely of hydrogen and helium, the simplest elements created in the Big Bang, with very little of the heavier elements, metals, necessary for rocky planets and complex chemistry. Without metals, early galaxies were unable to form dense, structured environments that are typical in star systems with planets like those in our own galaxy. These early galaxies experienced intense periods of star formation, often in sudden bursts. Massive, short-lived stars quickly consumed available gas, producing intense ultraviolet radiation that ionized surrounding hydrogen gas. When these stars exploded as supernovae, they enriched the surrounding interstellar medium with heavier elements, setting the stage for future generations of star formation with progressively higher metallicity. The dynamic, chaotic nature of these galaxies, and frequent collisions among them, helped fuel rapid evolution, leading to larger, more stable galaxies with complex structures over billions of years. An interesting note about our own galaxy being an outlier is that most of the dwarf galaxies we have absorbed have had their star formation virtually extinguished. Just the two largest dwarfs, the Small and Large Magellanic Clouds, have any significant star formation still occurring. The new Saga survey indicates this is atypical, and also that we have fewer satellite galaxies than normal for a galaxy of our size. Anomalies and outliers always interest us in Fermi paradox filter discussion. At the galactic year scale, where the equivalent to a day is almost 1 million years, it takes several years for a dwarf galaxy to merge, and as it passes through, you get these waves of star formation, and you get these short-lived giant stars lasting only a galactic day or two after formation before detonating as supernovae and leaving neutron stars and black holes in their wake. And events like this aren't terribly conducive to life surviving nearby, plus mergers will tend to set off quasars or their weaker form of active galactic nuclei, which also is not great for life. A key aspect of the Fermi paradox is trying to figure out when life first emerged, And if we are correct that interstellar travel is possible and can be made practical, and that technological civilizations are not automatically living on borrowed time before killing themselves off, or making something which does the job for them, then it stands to reason that intelligent life like us is a relatively new thing, as otherwise we would expect civilizations with head starts of billions of years to have settled every free rock in the universe. We would expect intelligent machines to do the same, so only if they're relatively dumb would AI matter for the Fermi paradox, something we'll examine in regard to zombie AI in a couple months. So we try to see what might have made life much harder earlier in the universe. Obviously, until the end of the photon era, about 400,000 years after the Big Bang, the universe was too hot and bright for any molecules to form, let alone life. Things were quite dark for many millions of years afterwards, as there were no stars. Those first stars formed around 100 to 250 million years after the Big Bang, and were population 3 stars with basically no heavy elements in or around them, so no planets or even wisps of rocky or icy bodies in which life might have formed, like comets. We may have had some weird options like dark matter stars even earlier, and if you're curious, see our episode Dark Stars at the beginning of time. Our own sun didn't form till 9,100 million years after the Big Bang, and Earth about 9,200 million years after the Big Bang. Between 250 and 9,200 million years, presumably some conditions changed, gradually or sharply, that started making life-bearing planets more probable. And keep in mind, if we assume maybe 100 such planets existed in our whole galaxy at 9,200 megayears, and we're all just hitting space now, maybe us first, you would need a sharp change to explain why no single planet formed at maybe 8,000 megayears, instead of 9,200, whose inhabitants had over a billion-year head start on settling this galaxy, and given the time involved, they could have developed over in Andromeda or even further away, and arrived here by now with time to spare. So, what changed? Today we're exploring the Fermi paradox and the critical role galaxies in their early history may play in the emergence of life. But what if the very air we breathe is the answer to why the stars are so silent? In this month's Nebula exclusive, Fermi Paradox Air, we dive into the mysteries of planetary atmospheres and their profound influence on life and civilizations. That's out now on Nebula, the largest creator-owned streaming service. Nebula offers tons of exclusive content from myself and other creators, like Faithless, a Sojourn story, and full-length episodes of SFIA like Fermi Paradox Air, which we release on the first day of every month. Plus, every episode of the show airs early and ad-free on Nebula. Using my code, IsaacArthur, you can get 40% off an annual plan. That's less than $3 a month, about the price of the drink or snack you've been enjoying during this episode. Lifetime memberships, gift memberships, and gift cards are also available, so you can share Nebula with friends and family. Sign up at go.nebula.tv/IsaacArthur and support this show directly. And don't forget to check out Faithless, a Sojourn story, a feature-length audio drama exclusive to Nebula. Follow Castrian Vadric's journey through the Sanctum as he faces ancient truths and battles to reunite with his beloved Valendra. It's a must-listen for science fiction fans. Again, that's go.nebula.tv/IsaacArthur. So, what changed? Well, our sun is a population 1 star, the younger kind with higher metallicity, formed out of a nebulae in which many generations of supernovae and stellar remnant collision had already occurred to create heavier elements. Older stars are called population 2 and are lower on metallicity but still have some, unlike population 3 stars. Metallicity incidentally is a measure of what proportion of a star is made of materials besides hydrogen and helium, which includes a lot of things not considered metal except in astronomy, like the carbon you and I have in our bodies. Pinning down exact metallicity is tricky since you can really only measure what the surface composition is, which for our sun is 1.34% of its mass as metals, then making estimates off its age, and we often just measure the iron to hydrogen ratio as it's easier to get and tends to match up well with overall metallicity, especially for initial metallicity given that iron only gets made when big stars die, and just minutes before. And planetary formation is based on those initial metals in the nebula the star formed from, since the planets will form with the same ratio initially. Once a star gets going, it begins fusing hydrogen and emitting solar wind, and that solar wind also blows lighter gases, particularly hydrogen and helium, out into deep space, so that only massive planets like Jupiter keep their initial composition. Hydrogen is very uncommon in our inner rocky planets, and helium virtually non-existent, especially in the context of both them making up about 99% of everything, not including dark matter of course, which we will discuss later. On this iron to hydrogen ratio chart, our own sun is set as 0, and anything higher than -1 is population 1, and anything beneath -1 is population 2. And a -1 would indicate a star with a tenth of our iron, and probably about a tenth our overall metals. It's a logarithmic chart, so a -2 on that chart would be 100th. A 1 on that chart would indicate 10 times the iron our own sun had, and no such star is known to exist, yet. The record is around 4 to 5 times our sun's metallicity, and that's uncommon even in new stars, and as a reminder, our sun is nearly 5 billion years old, so it is not young or particularly metal-rich anymore. It might have been when it formed though, and there are population 1 stars as old as 8 to 10 billion years, though they are not common. Also, the dividing line between metal-rich population 1 stars and metal-poor population 2 stars is rather arbitrary, again a tenth of our own sun's metal, which doesn't seem a healthy level for growing terrestrial planets. So we can't just say any population 1 star could have a good supply of rocky planets, while at the same time Kepler 444 is a metal-poor triple star system about 120 light-years from us, which is about 11 billion years old, which we think has 5 or 6 rocky planets of less than Earth's mass, each smaller than Venus but bigger than Mercury. And we can only see them because they are very close to their sun, so ultra hot, which means lighter elements all blew away. Considering that's within our own relative neighborhood of the galaxy, a place we might well have settled in this next millennia, it is probably not that uncommon in the wider galaxy. So on the one hand, we cannot assume metal-poor earlier stars had no rocky planets, and on the other, we shouldn't assume those early metal-rich stars that predate us by a few billion years were particularly metal-rich either, as they often would have had only a fraction the metals of our own sun. We probably shouldn't assume Kepler 444 is terribly normal either, but more to the point, we can't divorce its circumstance from it having planets. We don't really know much about exoplanets yet and what forms where, but that system is an orange dwarf, orbited by a pair of red dwarfs, out further than Pluto would be, and its furthest rocky planet is still so close to it that it would be intolerably hot. This is not a viable system and probably never was, and that layout of planets may be related to how a metal-poor system like this got them in the first place. We also have to acknowledge that you could have a nebula that was fairly metal-rich and be fairly old, just from an awful lot of supernovae happening there. Supernova candidates live in the low millions of years, not billions, so sharp periods of star formation and detonation could give you metal-rich regions rather quickly. In this same way, a planet forming close to a star gets boiled down, so a planet as big as Jupiter that formed from only 0.3% of its mass being metal could still be from a population 1 star system. And if all that hydrogen and helium baked away, you get left with an Earth-mass planet that's no more habitable than Mercury, whereas one further from that star may be in the habitable zone, simply retains its large amount of hydrogen and helium, and isn't a rocky planet. Stars also get hotter with time, so there's not many scenarios for a rocky planet getting baked out of an early gas giant and then becoming habitable later. But planets migrate, so a planet might get cooled down, but then it needs to get air and water again, and that will require an impressive cometary bombardment. But we think Earth got one, and a planetary migration could trigger a heavy bombardment period. Indeed, we think Jupiter might have migrated fairly close to Earth, then back again early in the solar era, triggering such a bombardment. Thus, metallicity is a decent filter for the Fermi paradox, but also doesn't seem sufficient by itself to prevent life arising billions of years earlier than it did on Earth. Galaxies also vary in metallicity by region as much as by age, and age also varies by region. Planets around a star are not necessarily the original planets of that system either. We do get a lot of migration and ejection scenarios, but more importantly for our discussion today, systems migrate around galaxies. that could take them often through areas near intense radiation fields, or where young star clusters were undergoing high supernova rates, especially in denser regions of the galaxy like near the galactic core. Stars and black holes emit intense radiation that could strip atmospheres or irradiate nascent planets, making it hard for stable environments conducive to life being able to develop. So that removes a lot of stars from the equation too. But I also mentioned frequent galactic collisions and mergers. Those and other interactions with other galaxies stir up gas and cause bursts of star formation, but they also destabilize planetary systems and can send disruptive waves of radiation across the galaxy, hindering conditions for life. As a result, it might be that only bigger galaxies forming later are good candidates for life, after most proto-galaxies had started fusing together. That is a more recent event. The last really big merger for the Milky Way that we know of was with the Gaia Sausage, which is the sausage-shaped remains of a relatively large galaxy we merged with between 8 and 11 billion years ago. That added about 50 billion solar masses to our galaxy, roughly the mass of Triangulum, the only local galaxy besides Andromeda that we don't call a dwarf. Most dwarf galaxies we absorb now are much smaller, often under a billion solar masses, all the way down to things that border on being a globular cluster. Omega Centauri is a good example of a borderline case. Globular clusters are old and immense star clusters, often running into the low millions of stars, and none would be great candidates for life. Dense star clusters, like globular clusters, but not limited to them, have intense gravitational and radiative environments. Frequent gravitational perturbations would eject or disrupt planetary systems, making long-term stability rare and reducing chances for life to begin, let alone continue and thrive. A lot of them have retrograde orbits too, going backwards from how the galaxy spins, which we tend to think indicates we picked them up from other galaxies we absorbed, since many would have had different spins than us. Galaxy mergers are long events that also trigger star formation, as well as probably kicking off new rounds of ejections that might strip planets off stars or cause stellar remnants to migrate into other systems to explode, or cause the core of a galaxy, where there's usually a giant black hole, to get a wave of matter that can activate a quasar. Quasars were a lot more common and brighter in the past, peaking out around 10 to 12 billion years ago, and have slowly grown less common since. No galaxy is going to be very hospitable to life during this period. They may be nearly extinct by now, especially the really big ones that would auto-kill life. What remains are much quieter and weaker ones. They are very uncommon closer to us, and the nearest is Markarian 231 at 581 million light-years away. They are also intermittent, usually lasting 10 to 100 million years, so you could have easily had circumstances in most galaxies where until maybe 5 billion years ago, quasar periods were just too common for most galaxies to have had life develop and stick around. It is likely that the Milky Way was once active as a quasar, particularly in its early history, several billion years ago. Evidence suggests that the supermassive black hole at our galaxy's center, Sagittarius A star, experienced phases of much higher activity, potentially enough to resemble quasar-like behavior. One clue supporting this theory is the presence of Fermi bubbles, large structures of gamma-ray emitting gas that extend about 25,000 light-years above and below the Milky Way center. These bubbles may have formed from past energetic outflows from Sagittarius A star when it was actively accreting large amounts of gas. And yet this itself is a reminder that a quasar is not an automatic kill, as based on that evidence, it is likely our own galaxy went through such a phase as recently as 6 million years ago. It might be interesting if any extinction periods tracked that interval. I'm not aware of any, but it's not my field, so if you know of one, post it in the comments on the episode. Not all quasars are equal though. They can be 1 trillion times brighter than our own sun, and in deadly wavelengths. But the range in quasar from brightest to dimmest is around 1 million, and the ones that tops that range are going to sterilize galaxies, while the dimmer ones presumably do not. Again, we think only 6 million years since our last period as one. Bigger galaxies like ours also got that way by eating smaller galaxies, which is exactly what causes quasars, and yet those bigger galaxies have a lot more going for them as hospitable places for life. So it could be quasar and active galactic nuclei prevented habitability till the last 4 or 5 billion years. It may even have been the case all the way up to and after Earth formed, as life on Earth is estimated to be no older than 4.1 billion years, and maybe no older than 3.5 billion. But that would not be a universal state, even if our galaxy didn't calm down enough for life to exist till 3.5 billion years ago, and then with some luck, maybe over in Triangulum it was 5 billion, or some other place in the local galactic area. The nearest 1,000 or so galaxies could probably have colonized this galaxy by now if they had gotten to space even just 100 million years ago. What else might have put a timeline on life developing? Well, the density of cosmic rays, which would have been decreasing with time, could be a factor. Cosmic rays can interfere with chemical bonds, disrupting formation of stable organic compounds and creating environments too hostile for prebiotic chemistry to thrive. This could also cause instability of molecular clouds, the cooler, denser nebulae that stars and planets form from. Life requires stable regions in space, like molecular clouds, to form the building blocks of biology. In a young, turbulent galaxy, these clouds may have been too unstable or short-lived to allow for significant chemical evolution toward life. Early intense star formation might have released massive amounts of ultraviolet radiation, disassociating molecules essential for life, like water, on a galactic scale. This would hinder organic chemistry from getting a stable foothold across large regions of the galaxy. For that matter, since planets were usually millions of years younger than their star clusters undergoing lots of early supernovae might have had a lot of planet-forming material disrupted before that formation occurred. And again, not a very good strong filter itself, but we are seeing today a number of galaxy-scale conditions that are functions of time, being stronger filters the further we go back. If for the sake of argument we said a given filter was 0% 3 billion years ago and 100% 13 billion years ago, and was dropping linearly with time, 10% a billion years, that's not too hostile. If we had 3 overlapping conditions like that, then they stack so that instead of 10% it would be 27%, and at 20% that would be all the way up to 49% and rising sharply. And that's assuming a linear drop. It could be something more like a square drop, and so conditions even a billion years back might have been producing 1,000 times less stably habitable planets, so that we are a 1 in a billion case for life arising, where new planets forming the last billion or 2 years are just 1 in 100. If you then throw in all the other filters specific to planets and solar systems and dragging against the weight of time, we could find that life is just horribly improbable, and then the midterm filters further cut down the odds of intelligent life emerging. As we often note, people tend to assume evolution inevitably leads to brains, but I've rarely met a biologist who shared that opinion, and quite a few who think it was an improbable evolutionary path. Even the complexity of life itself beyond the microscopic was a pretty recent event, as we saw in our episode on rare complexity last year. For most of our planet's history, life was microscopic, and most of the life currently on this planet still is. But if life does get complex and smart and space-capable, like we seem to be, is that the end of it? Well, maybe. As we mentioned, we have late filters, like nuclear war, or AI, or space travel being impractical after all, but that would not seem galaxy-specific, would it? And the answer would seem to be mostly no, but let's close with a consideration that hospitable galaxies might be prone to having life pop up, but soon be replaced by artificial life. This is a topic we'll explore more this spring and flirted with last year in our discussion of interdiction bubble civilizations, but it may be that most civilizations aren't well suited for galactic expansion, but do get to the point that they are unleashing a lot of stupid robots or zombie AI. Normally, the Fermi paradox does not care about AI because a smart AI that wiped out its creator might be just as likely to explore and settle space itself, or themselves, and even if most did not, many might, and might also be better at it than organic life. But while human intelligent AI or superhuman AI is a real threat, we are starting to see a concern about dumber AI maybe being the real problem as it arrives, presumably first on the scene as a threat before smarter AI gets invented. And we'll deep dive that this spring as mentioned, but imagine a civilization does get to space and soon realizes it's a lot of effort and turns it over to robots, After all, we already use them in space far more than humans. Such being the case, you've got no real reason or method for preventing them expanding far past your borders. You could have the same hospitable galaxies that produce multiple intelligent species still around and kicking, but invisible from a Fermi paradox perspective because they do not expand out much into the galaxy, sending robots to do the work and not caring what happens to them once they get far enough out to be hard to utilize and control. They go and mine out systems and send it home. This might be a more normal scenario than species which are hyper-enthusiastic about colonizing a whole galaxy, and they might tend to then bump into those robot swarms a lot and get contained or slowed by them or even wiped out. We discussed that idea more back on Halloween in our Ghost Armadas and Ancient Galactic Wars episode, and to be honest, I do not think it too likely, but it is on the table. But perhaps a bit more disturbingly, if we assume a lot of civilizations arise and harvest parts of their galaxy and leave problematic machines behind in their wake as they return to their homeworld or settle some new reality or hibernate to a later era of the universe with their stockpiles or whatever, then instead of galaxies getting more fertile with time, as we tend to expect as metallicity rises and galaxies settle down, it may be that galaxies are getting less hospitable and more dangerous, as even those dwarf galaxies left untouched by luck get absorbed into larger ones and exposed to whatever mining and leftover robots prior civilizations left behind. Or they might have an effective half-life, left over from those dawn civilizations, and nobody could arise till all those finally broke down. Who knows, it might turn out that we were lucky to be born first in this galaxy, or it might turn out we were lucky enough to be born after the galaxy became a safer place.